Hi everyone. Welcome to another Graphs and Matroids seminar. Today we have Matt Sullivan from University of Waterloo, who's going to be talking about rotation systems and simple drawings of KN. Go ahead, Matt.
Thank you. So yeah, this is a joint work with Dr. Bruce Richter, and we'll split this talk up into two little sections, one on simple drawings and one on rotation systems. So before we even talk about any of that, maybe I should get you into simple drawings. So, there's this really common problem, or this really famous problem of rails and trains and suppose you're designing a circuit or a rail system, however, it's very expensive for you to have wires and rails cross, then it would be very useful to be able to solve one of the following problems. So the crossing number problem is that you're given a graph G. What is the minimum number of pairwise edge crossings required to draw G in the plane? Okay, and then of course, if you're given a graph G, output a drawing D that has the minimum number of pairwise crossings. So in general, this is an extremely hard problem. And even for complete graphs, the answer is unknown. And so this is an open problem right now. It's known as the Harari-Hill conjecture. And it's conjectured that the minimum number of crossings over all drawings of Kn is the following. And this has been opened for over 50 years. I think right now, the best lower bound is a multiple of it's like 99% close to that number. And I think, and of course we have drawings achieving that number. In particular, if you take a tin can and put n over 2 vertices on the top and n over 2 vertices on the bottom, and you just draw the shortest paths, then that'll give you a drawing of this many crossings. Okay, so let's talk about simple drawings of Kn. So first of all, let's define it. A drawing D of a graph G is said to be simple if each pair of edges crosses at most once, no two edges incident to a common endpoint cross, and no three edges cross at the same point. So here we have a picture of three violations, each one violating its respective bullet point. Okay, so we won't see much of this in this talk. However, at some point, I will be drawing non-simple drawings. So it is important to know these things. Okay, so here as an example, we can enumerate the unlabeled simple drawings of K5. There are exactly 5 of them. The first one being 1 crossing, the next 2 having 3 crossings, and the final 2 having 5 crossings. So here are some facts about simple drawings. Don't worry, you don't need to remember any of this. This is just some fun. So if D is a drawing of the complete graph and R is a face in D, and we're just going to label BR as the boundary of a face, then for any edge E in the complete graph, E intersect the boundary of a face is a subset of the endpoints of E or is a single connected segment of E. And so what we're learning here is when you look at the intersections of edges and faces, an edge can't intersect a face like 5 or 6 times or 10 times or 20 times. For any vertex V in Kn, at most 2 edges incident to V intersect the boundary of a face at more than just their endpoints. So yet again, you can't have 3 edges incident to V intersecting a face a lot of times. So a really interesting result this is just an extension of Cairo-Theodori's theorem to simple drawings of Kn, and this was shown by Balco, Fulek, and Kinchel in 2015, is that if R is bounded, so R is a face and it's the bounded side of that face, then there's a 3 cycle in Kn containing R and its bounded side. And it doesn't seem so crazy, but as a corollary of this, every face in a simple drawing of Kn is the unique open intersection of sides of 3 cycles over all 3 cycles in Kn. So that sounds fairly strong, but we will see an application of this in this talk. So like I said, the first 2 bullet points, actually, you don't need to remember at all. That's just to say that when I draw things, my drawings are fairly general. And the last 2 bullet points, I will use those later on, and you'll see how they're used. Okay, so I'm going to define what a Reidemeister 3 move is. So we have 2 pictures here. A Reidemeister 3 move comes from knot theory, and it's on a triple of pairwise crossing edges, and it's the action of moving one edge over the crossing of the remaining 2 without crossing anything else in the drawing. So we have a picture on the left here. It has 3 red edges, and I have that sort of arced horizontal edge above the crossing, and then I move it below the crossing in the second picture. And that's a Reidemeister 3 move. And you can notice that there's kind of this, closed curve defined on those 3 edges that bounds a face. And so you could really only do Reidemeister 3 moves over faces. Okay. So here we're going to have our first theorem, and it's the characterization of edges and faces theorem. And it says that we let n to be at least 4, and d be a simple drawing of Kn. If C is an edge of Kn and P a point in a face of D, then either there's a sequence, possibly empty, of Reidemeister 3 moves on D that places C on the boundary of the face containing P, or there's some drawing, fancy D of D, on a K4 containing C, such that no face of fancy D contains P and has C on its boundary. So you have a K4 separating P and C, or you can do Reidemeister 3 moves to bring C to the boundary of the face containing P. You only have 2 options. Okay, so we'll show an example of this, of course. Here's K10, a drawing of K10, and here's a face. Okay, and let's look at, say, the edge 3, 9. So I can either apply Reidemeister 3 moves to this drawing, so that I bring 3, 9 to sort of that blue colored region, or there must be a separating K4. And here is my separating K4, and so that's sort of the idea of the theorem. Okay, so let's try to prove this using illustrations. We're going to let R sub P be the face initially containing the point P, and assume the edge UV is not initially on the boundary of R sub P, because if it is, then it satisfies the first bullet point if I just let the sequence of Reidemeister 3 moves be empty. It's already on the face, so we're going to assume it's not on the face. Now, when I say on the face, I mean like not at its endpoints, and so the intersection of UV with the boundary of the face could be at the endpoint U or the endpoint V or both. So we're going to break this into cases. If that intersection is not empty, then it's at one of the endpoints, at least one of the endpoints, I should say. So in my picture here, I have U on the boundary of R sub P. Note, I did not draw the vertex V because V could be on R sub P. It could not be on R sub P. We don't really care. However, it's important to note that U has 2 incident edges, UZ1 and UZ2 on the boundary of R sub P. And in particular, when you look at the K4 involving U, V, Z1, and Z2, it looks like one of the 2 drawings. And in both of those drawings, no face has 3 edges incident to U bounding that face. So we just look at the drawings of the K4s and go, oh, look, like, 2 edges bounding this face are incident to U, and do that for every face. You'll see that at most 2 edges incident to U bound that face. So since UZ1 and UZ2 already bound R sub P, it tells us that UV does not bound R sub P, and in particular, that K4 separates UV from R sub P. Okay, so that's actually a proof that UV has empty intersection with R sub P. And then we're going to ask, so it has empty intersection, is there an edge like X1, X2? In particular, is there an edge X1, X2 on the boundary of R sub P, not just its endpoints, that crosses UV? If such an edge exists, then from X2, we can go to the boundary of R sub P, and that's a crossing. And so there's another edge there, Y1, Y2. And there are lots and lots of options for Y1 and Y2. It could look like, it could just not cross UV at all. We could extend from the vertex y1 and cross UV in that fashion, or this fashion, or even that fashion. I claim that in all those cases, there's always a separating K4 involving UV and two of those special vertices. So two of x1, x2, y1, y2. We won't go through that. It's kind of boring. Just believe me. Now, there are more options, of course. I extended the edge y1, y2 from the segment starting at y1. We could have also extended at y2. Similar thing happens. You always get a separating K4. There is, however, one interesting case, and that interesting case is the following. When y1, y2 crosses like this, then we have this beautiful orange triangular region, and you can kind of imagine that it looks like that you can already apply a Reidemeister 3 move to UV to bring it to the boundary of R sub P. Now, there could be some problems. Of course, there could be a seventh vertex out of nowhere that's in this orange region. And again, that's another one of those cases where, okay, there's going to be a K4 involving Z, U, V, and one of X1, X2, Y1, or Y2 separating UV from R sub P. So we won't worry about that. Alternatively, there could be an edge that crosses this orange region. And so the question becomes, what should we do if an edge crosses this orange region? So if that's the case, we'll pick the closest such one to the boundary of R sub P and apply Reidemeister 3 moves to it until it goes onto the boundary of R sub P. And so we actually just eventually bring it there. I'm not going to explain why you could do that, but it's fairly straightforward. Okay, so once we bring G to the boundary, we apply the same analysis to G and one of x1, x2, or y1, y2. So if we look at the new boundary of R sub P, and you look at the edges that are on it, it goes x1, x2, and then G, and then y1, y2. So you just apply the same analysis, replacing x1, x2 with G, or y1, y2 with G, and you either get a separating K4 from all the previous cases we've done, or you can do this over and over and over. And so these Reidemeister 3 moves will be the exact Reidemeister 3 moves described in the theorem. So eventually you will empty this orange region and you'll be able to bring the edge UV to the boundary of R sub P. Okay, so what does that leave us with? So going back a second, this is all on the edge x1, x2. Does an edge like that exist? And so what we're going to try to show is you have a face. There's a graph that induces that face. And so we look at the graph that induces that face plus UV. Okay, and we're going to look at the drawing of that graph. We're going to call that drawing D sub P. And for every case in which that we haven't covered, in which something crosses UV in that graph, there's, other than what we've covered, there's always a K4 separating UV from R sub P. So we won't cover any of that. Just some tedious case analysis, no fun, fair enough. So we're going to assume that UV is uncrossed, okay? In particular, it's on the boundary of exactly two faces, F1 and F2. Okay, so in this instance, this is where our corollary of Caratera-Dori's theorem comes in. And that theorem says that every face in this drawing is the unique open intersection of three cycles in the graph. In particular, those three cycles could use the edge UV or could not use the edge UV. Now when comparing F1 and RP and F2 and RP, if both those three cycles contain UV, then it looks like this, or a version of this, I should say. And we can see here, if you combine, so I guess I should give it a description. The blue three cycle along with UV separates F1 and R sub P, and the red three cycle along with UV separates F2 and R sub P. And so the K4 involving the blue and the red and UV clearly separates R sub P from UV. And so that we would be done. So one of those 3 cycles must not use the edge UV. And if it doesn't use the edge UV, it means that it separates both the faces from R sub P. So we would think this is good. However, we have 5 vertices here. We have 3 vertices in this blue 3 cycle, and we have 2 vertices, U and V, so that would be a K5. And so we want to do analysis on that K5. So we're going to narrow in there. We have our blue 3 cycle, our edge UV on the inside, and the face R sub P somewhere on the infinite face, okay? And we ask, how are the edges drawn? So if all the edges to U from the 3 cycle are drawn inside the 3 cycle, then it's fairly easy to find a separating K4. In particular, in this drawing, we have this highlighted yellow region using 2 of the vertices of the 3 cycle along with U, and just throw V in there for fun. That's a K4, and that K4 will separate RP and UV. Okay, so that tells us that one of the edges from the 3 cycle to U is not drawn inside the 3 cycle. And there's one way to do that. And in this instance, we've just partitioned the infinite face into 2 different faces. And so R sub P could be in either the infinite face now or this new, bounded face. And now we need to find 3 cycles like we did before. So if R sub P is in the infinite face, here's your 3 cycle, add V to it, and now it's a K4 that separates R sub P from UV. And alternatively, if R sub P is on the inside, here's your 3 cycle, add V to it, there's a K4 separating R sub P from UV. And so that actually finishes the proof of that characterization theorem. And I personally think it's a really neat little theorem. And we'll actually use this to prove the main result on complete rotation systems. However, I haven't even talked about rotation systems yet, so let's do that. Okay, so first of all, let's introduce it. So here we have a labeled drawing of K5. And for B, C, D, and E, I've outlined the cyclic clockwise rotations around that vertex. And so for the vertex A, we can do the same thing. Pick your favorite starting point. Let's say we start at B. And I'm going to outline the cyclic ordering around A going clockwise. So at A, it's B, and then C, and then D, and then E. So we call this the rotation at vertex A, and the group of such rotations is called the complete rotation system of the labeled K5. And of course, we can generalize this to complete labeled KNs and drawings of that. We can get rotation systems from it. So this is a great description. So that's exactly what a rotation system is. It's permutations of n-1, cyclic permutations of n-1 elements. So in particular, does every complete rotation system have an associated simple drawing of Kn? Now, the answer is going to be no. On the right-hand side here, I have a 4-vertex rotation system, and I've tried to draw it. Unfortunately, I cannot draw the edge 3, 4 because it will violate the fact that the resulting drawing would not be simple. So I cannot draw this rotation system in a simple fashion. However, when you can, we call the complete rotation system realizable. Okay, so do complete rotation systems encode the oriented crossings of edges? And the answer is actually yes. For every realizable rotation system on 4 vertices, there is a unique labeled K4 for it. And in particular, for every realizable 5-vertex rotation system, there's still a unique, for every realizable complete 5-vertex rotation system, there's still a uniquely determined labeled drawing. Okay, and so you can get oriented crossings. In the K5, the order in which 2 edges cross a third is determined. Lots of things determined. Okay, so for our purposes, we're going to need this definition. So we define a complete rotation system, H, to be an NK rotation system if H is a complete n-vertex rotation system and every k-vertex rotation system in H is realizable. Okay. So more natural questions. Is every N4 rotation system realizable? The answer is no. Here we have a picture of, well, first on the right-hand side, I have a 5-vertex rotation system. I promise you every 4-vertex rotation system in it is realizable. I won't show it. And I try to draw it. So I drew the K4 involving 1, 2, 3, 4. And then I started to draw the edges incident to 5 with the red segments. And you can't complete that to a simple drawing. And so that shows that this is going to be not realizable. In particular, there are 2 5-4 rotation systems that are non-realizable. Interesting fact. So how do we tell if a complete n-vertex rotation system is realizable? So Kinchel in 2011 showed that every n6 rotation system is realizable. And he actually did this on a set of more general objects called simple abstract topological drawings by using homotopy. So unfortunately, this proof is not well understood combinatorially, and it can't even be extended to N5 rotation systems because he has an example of a 6-5 simple abstract topological drawing that is not realizable for him. So, but it doesn't extend to a rotation system. So now, through personal communications with Alsman Eicholzer, he has shown computationally that every 6-5 rotation system is realizable, motivating one of the main results of my thesis. And we show combinatorially, not using homotopy, that a complete rotation system H is realizable if and only if every at most 5-vertex complete rotation system is realizable. Okay, so don't let this confuse you. Of course, drawings are not determined by their rotation systems. And here is an example. We've already talked about Reidemeister 3 moves. So on the left-hand side here, I have a drawing of, again, K6. I've highlighted the red edge 3-6, and you can apply a Reidemeister move of 3-6 over the edges 1-4 and 2-5. And this creates a different drawing. However, it does not change the rotation system. And so this is an example of a rotation system not determining its drawing. Okay. All right, so let's prove a weaker version of the characterization of realizable complete rotation systems. In particular, let's show that every N10 rotation system is realizable. Now, a crucial point in this theorem is deciding the order in which a directed edge, UV, crosses the other edges from an N10 rotation system H. To find such an ordering, we must observe how the 10-vertex complete rotation systems involving E and 2 other edges in H are drawn. And this is probably the most technical part of the talk. So we have this edge ordering lemma here. It's fairly simple. All it says is that if you have an N7 rotation system, and by definition, an N10 rotation system is an N7 rotation system, containing 3 edges, E, F, and G, that both cross E, and E is going to be a directed edge. Then in any realization D of H, the order E crosses F and G is determined in D, or there's a sequence of Reidemeister 3 moves on D, such that the last Reidemeister 3 move is applied to the edges E, F, and G. Now, the Reidemeister 3 move, we'll see it in a second, but when you think about it, when you apply a Reidemeister 3 move to a triple of edges, you're actually switching the order those 2 edges cross on the third every time. And so this is why Reidemeister 3 moves, if you could do a Reidemeister 3 move, the order of the edges is not determined because you're swapping the orders. So if you have 2 edges, there's lots they could do. So far, these 2 edges cross the edge E, or in this particular instance, they cross the edge UV. Now they could share an endpoint, and if they do share an endpoint, then you're dealing with 5 vertices in a rotation system. And I already told you that 5 vertex rotation systems that are realizable, their drawings are uniquely determined. And since they're uniquely determined, the order in which the edge UV crosses F and G is determined. So what we're going to do is, if they share an endpoint, we're just going to call this ordering the wedge relation. The F is wedge related to G. And in this picture, UV crosses F then G, and so F is less than G, or less than wedge G, if you want to call it. Okay. So if they do not share an endpoint and do not cross, which is completely determined by the rotation system, then they're ordered by this sort of wedge relation. And here's an example. You can look at the picture here, and going from U to V, we cross F, and then F1G1, and then F2G1, and then G. And in particular, F and F2G1 are wedge related, and F2G1 and G are wedge related. And so that gives us that wedge ordering. Okay, so like when are they not wedge ordered and not sharing endpoints and not cross? Well, there's only one way to do that. It's when you cross them consecutively. You cross F and then G. And there's actually only one way to do that in a drawing of K4. It's when the K4 is crossing and you pick a matching in that K4. Now, the oriented crossing of UV with F and UV with G is going to determine which of F or G you cross first. And you can see in this picture, starting at U, you cross F from inside the crossing to outside, and then you cross G from the infinite face back into the crossing side of that 4 cycle, F1, G1, G2, F2. And so the oriented crossings will completely determine which one you cross first. So when we have this picture, we're going to call this the parallel relation, or in particular, in this picture, we have F is less than G over the parallel relation. Okay, so there are other options for F and G. They could actually cross, and if they do cross, they could cross in a weird fashion. They can cross in such a way that all 3 edges pairwise cross, they form a closed curve, and no side of that closed curve is empty of endpoints, like we have here. Now, it turns out when you have this picture, we're thinking about simple drawings, there's actually only one way to draw the edge F1G2. The only way to draw the edge F1G2 is like that. And in this drawing, now we can see that F and G are going to be wedge related. In particular, F is wedge related with F1G2, and then F1G2 is wedge related with G. And so we're not going to worry too much about this picture because there's a wedge relation here. And now they could cross in such a way that the closed curve has a side with no endpoints, but there could be some other vertex in there. Now, in this instance, there are options for how F1Z is drawn. There are options for how G1Z is drawn, even G2Z and F2Z. But no matter what you do, there will always be a wedge and parallel relation between F and G. So in this instance, if we look at this example here, we have F is wedge related with F1Z, and F1Z is parallel related with G1, G2. I guess that's kind of a lie. I haven't drawn the entire K6 involving F1Z, G2, G1, and E, but if they're not parallel related, we learned that they must be wedge related. So in that K6. So it's either there's lots of wedge relations there, or there's a wedge relation and a parallel relation. Okay, and so the final option is that there's no vertex in there. So there could be, these edges crossing the closed curve like this, and this is where the Reidemeister moves come in. So in particular, in this instance, we would Reidemeister move some of the red crossing out of the empty side of the closed curve. And we would start bringing some of the red edges out. We bring the other red edge out. And at this point, we can ignore the red edges because they're no longer inside the closed curve. And we can ignore the endpoints of UV. And we could imagine that we would just Reidemeister UV out of that triangle area. And so you can see here in particular, the order of F and G on UV is F and then G, but then we do a Reidemeister move, it's G and then F. And so that's a pictorial example of Reidemeister 3 moves, like not determining, or sorry, stopping our ordering relations. But that was it. That was our edge ordering lemma, because it said that the only bad thing that that stopped us was Reidemeister moves, Reidemeister 3 moves. And so we have this edge ordering lemma, and we want to find an order in which E crosses edges of H. So what we've learned is that for any given two edges, F and G, the ordering lemma tells us that their order is determined on E up to Reidemeister 3 moves. Now, it would be great. Let's remind ourselves, what is our goal here? Our goal is to, we're trying to prove that N10 rotation systems are realizable. So we're assuming any complete 10 vertex rotation system is realizable. And so our goal is to find an ordering of that E has to cross of edges. So for three edges, F, G, and H, if F is less than G and G is less than H, then by the edge ordering lemma, this happens respectively in a 7 vertex rotation system. You combine those two 7 vertex rotation systems and you get a 10 vertex rotation system. Because, I mean, if you did the counting, it works. You get an at most 10 vertex rotation system. So in that realization of that 10 vertex rotation system, you're gonna get F is less than G is less than H. So you're gonna have a picture in which E crosses F and then G and then H. Now, when you look at how F and H are ordered on E, it must be the case that it's not, that they don't have a Reidemeister move, because it's their order is fixed in that 10 vertex rotation system. In particular, there's going to be some wedge relation or parallel relation or some pairwise, everything is crossing in a vertex in the middle, and that's all going to be in a 7 vertex rotation system, and there will be a 7 vertex rotation system showing that F is less than H. So this transitive property is actually going to tell us that we can find a partial ordering on the edges that extends to a total ordering. And that's all we were looking for. So that's the end of the technical bit. So what we know now is that if you're given an edge E from the rotation system, we can determine the order in which it crosses all other edges in the rotation system. All right, so our goal is to show that every N10 rotation system is realizable. And let's look at an example of how to do this by drawing a graph. So right here, I have a K7, and I want to show you how to draw the edge 4, 8. So from the rotation system, you just look at the rotation at 4, and it tells you where you start. In particular, you start between 1, 4 and 4, 7. So if you look at the rotation system, it's 1, then 8, then 7. Okay. And then our edge ordering lemma will tell us which edges to cross next. In particular, our edge ordering lemma will tell us, hey, you cross 3, 5 next, and then let's just cross it because we're supposed to, and it's on the boundary of the face we're in. Yet again, you cross 3, 6, it's in the boundary of the face we're in. That's great. Cross 2, 5. And then we come to an instance where we have to cross 2, 6. But the edge 2, 6 is not on the boundary of the face we're in. And this is where the characterization of edges and faces comes into play. Because since we're dealing with an N10 rotation system, in particular, every complete 10 vertex rotation system is realizable. Or in this instance, all we really need is 6 vertex rotation systems to be realizable. There can't be a separating K4, because a separating K4 would involve that K4 plus this blue edge, that's 6 vertices, and the orange 2, 6 edge would not be the next edge to cross. So since there's not a separating K4, there must be a set of Reidemeister moves to bring the edge you want to cross to the boundary of the face you're in. So we do that. We do those Reidemeister moves, and we can completely just follow along this lemma, or this this algorithm. So we keep on crossing edges until we finally come to our vertex. And of course, I can smooth that out. So I did that with one edge. I did that with the edge 4, 8. The real question becomes, can anything bad happen if I try to draw the edge 3, 8? The answer is yes, bad things can happen. And so let's talk about that for a second. So if we want to draw, I'm going to start drawing the edge 3, 8 from the vertex 8. I start drawing, I come into some face, and the next edge I need to cross is the orange edge. And the edge 4, 8 is blocking me. I can't cross 4, 8, because if I cross 4, 8, then I'm no longer simple, right? Edges incident to the vertex 8 can't cross each other. So what do? The trick is we just don't care. Like we just cross the edge 4, 8, and we keep on drawing and we keep on going. And our goal is to just get a drawing, no longer simple, just get a drawing of, you know, K8, say in this instance, that has all the rotations of every vertex correct. Except for maybe not the vertex 8. I don't care about the vertex 8, what the rotation is. And I'll tell you why later. So we just keep on drawing, we don't care, and the end result is we get a non-simple drawing with the edges incident to vertex 8 being tangled, and the rotation at every vertex being the same as in the associated complete rotation system. Okay, so now we have to deal with tangling edges. Tangled edges. So that's where this lemma comes in. If you have a drawing D of a graph, just two edges. The edges are U1V and U2V, and they cross. So obviously it's not a simple drawing. Then there exists a face R and D whose boundary is exactly a continuous segment of U1V and a continuous segment of U2V. So exactly like the picture I have here, this happens. And this can be proven pretty much using induction. It's a fairly short proof. All right. So we have these nice like segments of 3, 8 and 4, 8, and they cross like this. And the endpoints of 3, 4, and 8 are outside of this closed curve here. And this is going to happen in our bigger drawing. Now, in our bigger drawing, of course, the vertex, there could be a vertex in there. It could be vertex 6 or 5 or 1, whatever. I'm going to pick number 6. And we know that the edges incident to 6 are drawn in a simple fashion. The only tangled edges are the edges incident to 8. And so the edge 6, 4 has to be drawn somehow, and the edge 3, 6 has to be drawn somehow. And so in particular, to keep it simple between 3, 6 and, well, 3, 6 can't cross 3, 8 because then that would violate the fact that those edges are drawn in a simple fashion. Similarly, 4, 6 can't cross 4, 8 because those edges are drawn in a simple fashion. The only tangled edges are edges incident to vertex 8. So what we've drawn, though, satisfies the rotation system. In particular, the rotation system will tell us that 6, 4 crosses 3, 8 and 3, 6 crosses 4, 8. But that means there's 2 crossings in the same K4. In particular, in the K4 involving 3, 4, 6, and 8, we just found 2 crossings. And it says that's what our rotation system tells us. That just can't happen. So that's a contradiction. So that tells us that vertex 6 cannot be in there. And in particular, no vertex can be in there. So that's really good, because now all it leaves us with is an edge possibly crossing both those segments. Now, if an edge crosses both those segments, we're kind of happy. We don't really care, because now we just start to untangle these edges. You know, so we have these dotted lines here from 4 to 8, and we replace our edge 4, 8 with the above dotted line, and we replace the edge 3, 8 with the below dotted line. And notice the 2 dotted edges, they don't cross. They still both cross that big edge that crossed the closed curve, but they pairwise don't cross. Or sorry, they each don't cross each other. So you're actually reducing the number of crossings between edges incident to 8. And so you can see, if we kept on doing this, you can get a simple drawing in which no edges incident to 8 cross. Now, the one sort of stipulation here is it could have been possible that this will change the rotation at vertex 8. It won't change the rotation at any other vertex. It could change the rotation at vertex 8. Yes, so if it does change the rotation at 8, should we worry, should we not worry? And the answer is we shouldn't, because the rotations at the other 7 of 8 vertices remain the same. They follow the rotation system on those 8 vertices. And so it turns out that the vertex, so if you have a simple drawing where 7 vertices have the correct rotation, then the 8th vertex will always have the correct rotation. And that's sort of like the really cool thing here, is that no matter what we do to the vertex 8, change its rotation system, if we end up with a simple drawing, we're done. And so that's sort of the entire spiel. You know, here's our K8. We untangle all the edges. We can get an entire drawing of that K8, and that's how you draw your K8. Now, I did say I was going to talk about N10 rotation systems being realizable, but we could just generalize everything I just said to higher vertex graphs. So, like, you know, for any size n, that algorithm actually works. Plus or minus some details that I didn't include, of course. And I think that's everything. Thank you.
Thank you, Matt. Let's everyone please unmute, and we'll do a round of applause. So I'll count to 3 and then we'll clap. Okay. 1, 2, 3. Awesome. Okay, does anyone have any questions for Matt?
Yes, Henry. Oh, or maybe that was a clap.
If there are any, you can just unmute and ask your question.
Yeah, I had a quick question. So you had an example of a rotation system where there are 2 different ways to realize it, but
yes.
it was just because of one of these Reidemeister moves.
Let's see if we could back it up here. Yes, you're right. You're correct.
Yeah, I mean, but is that really all that happens, or are there examples of
so yeah, that actually is all that happens. That's actually known as Jones' theorem. And Jones' theorem says that if you have 2 simple drawings of Kn that have the same rotation system, that they're the same drawing up to a set of Reidemeister moves.
Nice.
And you could actually prove that. So that's another part of my thesis, is I give another proof of Jones' theorem, because you can actually prove it using the same method of just like draw the edges one at a time, and you know, wherever 2 drawings differ, you prove you can get from one to the other using a set of Reidemeister moves.
Does anyone else have any other questions?
Are there analogs of the Harari-Hill conjecture for other natural classes of graphs?
Yeah, so there's also the, I'm probably going to butcher this name, but the Zarankiewicz conjecture, I think, and that's on complete bipartite graphs, which is also still very much open. And they have like, in terms, so let me, can I exit? There we go. Come out of presentation. Or maybe I'll just go back this way. So we'll come back here. Yeah, so the numbers for complete bipartite graphs are actually very similar to these right here. I can't remember what it is. Off the top of my head, I can't remember what they are, but it's very similar to the Harari-Hill conjecture in terms of the numbers.
Do you think rotation systems could be modified to apply to complete bipartite graphs?
That's for complete bipartite graphs, no, because as soon as you start like removing edges from your complete graph, rotation systems tell you very little in terms of how the graph is drawn. Like, and I think Alan Arroyo and Austin Eicholzer and maybe like Irena Parada showed that, what was it? As soon as you remove more than a matching out of the graph, then there, like, the number of possible drawings becomes like extremely large. Yeah, and so like we're hoping that rotation systems will at least help us for the Harari-Hill conjecture, right? Because for a rotation system, you can say when a K4 is crossing, right? So computationally, you can put it into a computer and say, what is the crossing number of this rotation system? And, you know, is it this? So yeah, a lot of the current algorithms now for like trying to compute the crossing number are just rotation systems, and they just do like kind of brute force, is every K5 realizable? Like, is every 5 vertex rotation system realizable? If the answer is yes, then it says compute like crossing number of that rotation system, and that's the rotation, the crossing number of that associated graph. Yeah.
How fast are these algorithms?
So right now we know, so okay, published results, we currently know the crossing number of K12. However, this like recently, like I think the past month or two, Oswin just finished his, like the results just came out for K13, which also implies K14. There's like a reduction there. So now it's open for K15.
Wow.
It was confirmed that all of the crossing numbers of Kn up to 14 is exactly the Harari-Hill conjecture. So nothing, you know, no contradictions or anything. Yeah.
Last chance for questions. I think that's good. Thanks again, Matt. That was excellent.
Yeah, no
I'll stop the recording there.